Welcome to Brain Vision.
In this problem, we're asked to determine the radioactivity, R, of a banana that contains 420 milligrams of potassium. In potassium, it's potassium 40 that is the radioactive constituent, the radioactive isotope. And if you look up in Appendix B, the percent abundance of potassium 40 is 0.0117%. The half-life of potassium 40 is 1.248 times 10 to the 9th years. So in order to find the radioactivity of the banana, we will need to first find the decay constant given this half-life. We will also need to find the number of nuclei of potassium 40 isotope that's present in 420 milligrams. So in order to find the decay constant, we have a formula here that in which the natural log of 2 is in the numerator and the half-life in terms of seconds is in the denominator. We're given a half-life in years, so we'll have to convert it before doing the division. And the conversion goes as follows. We have the actual half-life in years. We multiply it by the number of days in a year and multiply that by the number of seconds in a day. Doing that, we get a result of, for our decay constant, of 1.79 times 10 to the negative 17th reciprocal seconds. Next, we need to find the number of nuclei in our 400 milligram sample of potassium with the abundance of potassium 40 isotope. Remember that we were given a percentage of 0.0117. So in order to have a fraction of that, we move the decimal point over to the left 2 decimal places. We multiply that by the amount of total potassium we have in our sample, which is 420 milligrams. This numerator is the amount of potassium 40 in milligrams. The denominator, we can approximate the atomic mass of potassium 40 using the atomic mass units, and the atomic mass number of potassium 40 is 40. This is an approximate. However, for this purpose of significant figures, it will do for us fine. And of course, we need our conversion factor going from atomic mass units to milligrams. That way, we're left with a unitless count of the number of nuclei. Plugging in these numbers, we find that there is 7.40 times 10 to the 17th nuclei. And finally, using the decay constant and the number of nuclei, we can compute the radioactivity of our sample. That is simply the product of the two. And from above, we have 1.79 times 10 to the negative 17th reciprocal seconds for our decay constant. And we have 7.40 times 10 to the 17th nuclei. Conveniently for us, the the powers of these exactly cancel, and if we multiply 1.79 times 7.40, we are left with 13.2 decays per second. And that's our answer.